Okay, so good afternoon, everyone. So today's this third lecture is on the radar and remote sensing. Is how we can use the radar devices for the remote sensing purpose. So first thing is what actually the radar can tell us. So yesterday we discussed about the functioning of the radar, like radar is working in the side-looking mode, and they are governed by two types of the resolutions, azimuth resolutions and the uh, range resolution, and the beam width is there, and their capabilities apart from the optical systems, like they are working in the side looking mode, not in the radar looking mode. Okay, and the radar is capturing the complex signals rather than the simple amplitude or real signals. So because of the complexity of the signals, we can derive two types of the information. Yesterday we discussed, like the amplitude as well as the phase information. So because of the complex signals, we are able to draw the amplitude as well as the phase. But apart from that, we did not discuss actually in radar systems, we are using, specialized electromagnetic radiations. So the ordinary radiation we are not going to use. We are using a specialized one, or you can say the polarized electromagnetic radiation we are using. So yesterday we discussed different types of the polarizations, like elliptical polarization, circular polarization, and the plane polarization. Okay, so whatever the signal we are using in the radar systems, they are the polarized signals, whether it is plane polarized or the circular polarized. But in space-based remote sensing, nobody has used the elliptical polarized signals. So here you can see the transmitted signal and the received signal of the radars can be characterized in terms of amplitude, in terms of polarization, in terms of phase and time difference, and the wavelength or the frequency. So wavelength is also one of the important parameter of the SAR signals. So in nutshell, we can say these four types of the information we can have with the radar signals. Means amplitude of the signal and the polarization, whether it is horizontally polarized, vertically polarized, or it is compact polarization, like combination of the plane and the circular. And the phase information may be geometrical phase, temporal phase, or the scattering phase. And the wavelength, like you are using the X band radar or the C band radar or L band radar, S band radar, P band radar. So basically, we are choosing a particular wavelength, or you can say the particular monochromatic wavelength or the frequency of a particular radar signal. So when we are using the radar devices in the remote sensing process, so these four types of the information are getting affected. So you can say if you are able to analyze how much effect is there in these quantities, so the effect in these quantities we can correlate with the changes or in the changes on the earth surface, means whatever the phenomena or the processes are happening on the earth surface. So because of those processes, certain changes can happen in these four characteristics of the SAR signals. So in the reverse way, we can say, if we know this particular process can affect this much phase or this much wavelength or this much polarization or amplitude. Okay, so if we know, let us say that is basically called the calibration part. So using the calibration process, we can understand, okay, this particular process can affect polarization of the signal by this much amount. Okay, and or the amplitude by this much amount, phase by this much amount, wavelength or frequency by this much amount. So if we have the satellite data, and from satellite data directly we can investigate, okay, how much changes we are getting in the data, and in the reverse way we can say this much effect is happening on the earth surface. So you can say these four parameters are directly linked with the processes or the phenomena on the earth surface. So that is basically the main purpose of the remote sensing. So in radar systems, we are using these signals, and these characteristics we are going to investigate. Whatever the changes we are observing, those changes we are linking with the processes or the phenomena happening on the surface. So that is very, very important things which we can tell from the radar data sets. Okay. And radar basically works very simple way, like the transmitted signal moves from the uh, satellite, or you can say from the antenna, and moves towards the receivers, towards the target side, and then after back scattering it is again moving towards the receiver side, and then we are observing basically amplitude, polarization, phase, and different wavelengths. So that is the standard process in the radar systems. So our ultimate goal is the investigation of these four types of the parameters. Okay, but in interferometry, one more parameter is there, that is called the coherence. Coherence means, because interferometry is applied not only in the single signal, that is applied over the two signals simultaneously. So we have to check whether both the signals are compatible with each other. Compatible means they are correlated with each other or not. Or you can say correlated means they should have the similar characteristics. Then only we can apply the interferometry. So that similarity, or you can say the correlation, but here we use the term the coherence. So the coherence between the two signals should be very, very high. Then we can measure the interferometric outputs very, very accurately. Okay. So in that sense, the coherence we can add as a fifth parameter for the radar, especially in the interferometric applications. So here you can again see, suppose this is the radar, and this is the radar, and different types of the targets are there on the Earth surface. So here you can see the pulses which are moving from the radar, like this pulse, then this next, then this next, then this next, fourth one, then fifth, then sixth, then in the seventh, you can see this portion of the pulse is basically interacted with this building or this target, and then it is starting, moving towards the sensor side. So you can say this is part of this is started going back, 7th, 8th, 9th, 10th, like that. And the other part of this pulse is further moving. So it is 8th, then it is 9th, then again from interacting with this is started moving towards the satellite. So this is the standard process of the radar signals that we have already discussed yesterday. Because of this side looking mode, the backscattered energy from different targets is reaching at different times to this receiver, and receiver is able to differentiate all the targets very easily, and hence it is the giving the very precise information of the position and the characteristic of the targets very clearly. So here you can see, if you see the pulse strength, means the intensity of the pulse versus time. So here you can see the initially and the pulse is very, very intensity is very low, and suddenly the strength is suddenly increasing. It means this strength is increasing because of some backscatter information received from this particular building. And then when the signal is moving this distance, then no other object was there, so the intensity started decreasing very rapidly. And then again, when it is interacting with this tree, then backscatter or the pulse strength is increasing, but not that much amount. So this is another indicator, means what types of the targets we have on the surface and what kind of the response of the pulse we can get. So here you can see this is a building. Building means some man-made structures. So man-made structures are basically fixed, or you can say strong, very strong. If some signal is coming, then these strong structures can reflect the energy very strongly towards the satellite. So since they are reflecting very strongly the signal, that's what the intensity of the backscatter signal is very, very high, because this structure is not going to change. But the same response from the tree, you can see, though the structure of the building and tree is almost, here it is looking similar, but the response from the tree is less or weak response compared to the building. So you can see very less amount. So we can also understand, or we should understand basically what is extra or what is not there in the tree as compared to the buildings, so that the response from the tree is weak. So that basically we can understand from the polarization part of the signals, or the roughness part of the signals, or the interaction of the signal with the natural environment or natural targets. So what is happening basically, because this tree structure is not very fixed, so that is somehow what is happening, some signal is penetrating inside the tree. That's what, when it is penetrating, it means then signal is not able to go back with that much strength, whatever is basically we are receiving from the buildings. So one is the penetration part, and because of these canopy structures, the signal is having the multiple bounces. Multiple bounces means the signal is first coming on, let us say, on this branch, then from this branch to this branch it is reflecting, then from that branch to this branch it is reflecting, and then again basically finally it is started moving towards the satellites. So multiple bounces are happening within the canopy structure, and because of that, at every interaction or every hit, the energy of the signal is going to decrease. That's what the overall strength of the backscatter signal is very, very weak. So from this particular example, we can understand a very strong response we are getting from the man-made structures, and weak response we are getting from the natural structures. So here only two examples are there, but in reality, number of variety of the features are there. Like somewhere water bodies are there, somewhere roads are there, somewhere agriculture is there, somewhere barren land is there, somewhere wetlands are there, somewhere oceans are there. Okay, so different types of the land use, land cover classes are also there. So we should understand which area or which types of the features can give which types of the response. If response is better, it means we can use them very clearly, or we can extract very useful information from these strong signals. But if your signal response is very weak, then there is a lot of uncertainty level in the investigations. So suppose your response is very weak, like in this case, and suppose further the response is very weak, then we are not able to differentiate what types of the features are there on the earth surface, and whatever the useful information we want to extract from the SAR signals, that useful information we are not able to extract just because of unavailability of the sufficient backscatter amount. Okay, so another parameter is surface roughness. Suppose surface roughness is smooth, or roughness is very rough, or smooth surface or rough surface. So from the smooth surface, some specular reflection happens, then backscatter amount is very weak. So that may be one of the reason. And if the surface is rough, then the backscatter amount is very strong. But this surface is rough or smooth, this is again depends on the type of the wavelength. Means if the longer wavelength can feel some the less rough medium roughness surfaces as a smooth surface. Okay, because means whatever the changes or the roughness is there on the surface, if that roughness is less than the wavelength of the signal, then the surface will appear as a smooth. If the changes of vertical change or horizontal changes are more as compared to the wavelength, then it appears basically the rough surface. So basically the roughness is in the relation with the wavelength which we are going to use. So you can say one surface may be rough for the smaller wavelength, but smooth for the longer wavelength. So just keep in mind, this is varying, and this depends on which type of the radar signal you are going to use. So here, these are some radar image parameters. So I have categorized them in two categories. One is called the system parameters or system properties. In short, I will now use the term SP. And another set of parameters is the terrain parameters or the terrain property like TP. Okay. So how basically these parameters we are going to investigate, or you can say why we are basically how we can understand the radar image quality is changing because of these parameters. Because the radar returns, or you can say the brightness of the radar images depends on these parameters. Now one by one we can understand how the system parameters are affecting the image quality or image brightness values, and how the terrain parameters are affecting the image quality. So here you can say within the system parameters, so within the SP, wavelength is there, polarization is there, speckle is there, beam geometry, and the spatial resolution. So beam geometry and the spatial resolutions, these are basically called the geometrical aspects of the system parameters, and the first three are called the radiometric aspects of the system parameters. Similarly, the terrain parameters are there. So those parameters are like surface geometry, that is geometrical aspect, dielectric properties of the target, that is radiometric aspect, surface roughness and volume scattering are the structural aspect. So we will see the effect of each and every parameter over the radar images. So here you can see the first parameter SP1, that is wavelength or the frequency. So in this image you can see this is the C band image and this is L band. This what is C band or L band? Actually, the as I mentioned yesterday, the microwave band or microwave wavelength is changing from 1 millimeter to 1 meter. So this range is further divided into so many sub bands like K band, Ku band, and X band, C band, S band, L band, P band, according to the wave increasing order of the wavelength. So, so the C band, L band, and P band. So you can say this is a C band image, and this is the L band image. So you can just check because both the images are of the same area, but you can check the quality of these images. Like here you can see these. Here the pixels are very dark, but here the darkness is not that much. Okay, and here this is dark and this is not that much dark. Okay, so this is because of the wavelength. Means if you are L band means longer wavelength, C band means smaller or shorter wavelength. So shorter wavelength or the longer wavelength, so the longer wavelength is giving much better result compared to the C band, because longer wavelength have longer longer penetration capabilities, and it interacts more with the targets, and hence more response we are getting in these SAR images. So that's what the response in L band image is better compared to the C band. And the below one, three images. First one is this X band, this is C band, and this is the L band. And this is BB polarization, this is HB polarization, and this is HB polarization. So here you can see the same area is there. So here you can see in the X band. X band means shorter wavelength. This area is just like dark, but this is C band. The wavelength of C band is larger than X band. So here you can see as the wavelength is increasing, so the darkness area is decreasing. And if you are increasing further the wavelength, then that area is removed. Now individual features are basically responding very well. So here you can also see this linear feature is very clear from here to here, but it is clear here but not clear here. But in this X band, this is not clear from here. So you can see according to the wavelength, what kind of the information we can extract. But here the ultimate thing is, if we are using the longer wavelength, we are getting better and better images. But this is not always true. Here we are getting better over this particular area. So basically this depends on your application. Suppose somewhere we will get X band better than L band, because X band is the higher frequency and L band is the lower frequency. So higher frequency basically attenuates frequently, but shorter frequency basically is not attenuating at a lot. Okay, so that attenuation is less in L band, attenuation is more in X band. If more attenuation is there, it means the image quality decreases. But if suppose the atmospheric conditions are very favorable, or you can say that is very clear sky is there, so atmospheric disturbances are very less. In that case, what happens, the X band will go to the earth surface and it will take more and more information, because this penetration capability with X band is less compared to L band. So this is not going to penetrate inside the earth surface. So whatever the actual thing is there on the earth surface, from here itself it can go back, or it can back scatter and reach to the sensor. So the actual information, or you can say the high resolution information, we can get from the X band chart. So in terms of resolution, you can say the resolution of X band is better than L band. This is again same scenario. Here you can see three bands are shown: C band, L band image, and the P band image. So the quality you can also observe if some features, if you are able to see, like this linear feature, and this linear feature here also, and here it is not clear. So in the longer and longer wavelength, it is not very clear. Okay. So this depends on the area where you are going to use these types of the information. And here you can see, here this area is dark, here it is very clear, but here it is again dark. Okay. So in the C band, this patch is appearing, dark, but here it is clear, here it is also clear. So this is basically depending upon the wavelength. And so how we can choose the suitable wavelength for particular applications? So here you can just consider these points. For higher wavelengths, more difficult processing. High wavelength means swath is high, and the pixel size is also high, and need larger antenna and the feeds. For higher wavelengths, we need basically the longer or larger antenna, and but simple electronics can also work. But for the low wavelength or the high frequencies, this needs the more power, because low wavelength means higher frequency. Higher frequency means H nu will be very high. So whatever the photon we are going to generate, so more energy is required for generating such photons. So that's what it is written, the need more power and need more difficult electronics, because this is high frequency electronics, so it is very difficult for development and in terms of cost also. And good component availability at the X band, this is also limitations. So here these are different applications I have mentioned according to the X band, C band, S band, L band. So starting from the ship detection, ocean feature, sea ice, oil spill detection. So many applications you can basically categorized, or you can select a particular wavelength for your particular application. Suppose you want the archaeological analysis. So for archaeological applications, P band is better. Biomass estimation, forest biomass estimation, again P band is better. Now recently the ESA is developing, P band radar specifically for the biomass retrieval at the global scale. So P band is better for the biomass estimation, but there are some limitations, because this P band is very close to radio waves, and these may have certain health issues on the earth surface also. That's what very limited use of P band radar is there, and no existing P band radar is there so far, but now ESA is developing. Now second parameter is the polarization. So polarization, as we have already mentioned, three polarization we discussed yesterday, but now here only plane polarizations are mentioned. Plane polarizations may be horizontal or vertical. So the in the radar images, polarization of the images is basically explained by these two digits. S stands for horizontal, V stands for the vertical. So first letter denotes or indicates the transmission of the signal or polarization of the transmitted signal, and the second letter denotes the polarization of the received signal. So if we say the HV polarization, which means the horizontally plane polarization radiation was transmitted, and vertically plane polarization was received. Okay, so first letter is the transmitted radiation, and second one is the received radiation. So you can say horizontally polarized, horizontally transmitted, vertically received, vertically transmitted, horizontally received, horizontally transmitted, horizontally received, vertically transmitted, and vertically received. So there are four combinations. So in all the polarization channels, if suppose the satellite is working in the fully polarimetric data acquisition strategy, then it means the satellite is acquiring the data in all these four polarization channels. Okay. So we will have one band for HV, another for BH, another for HH, another for BB. And for each and every polarization, there will be two things. One will be the real part, another one will be the imaginary part. So that we can say the signals are complex in nature. Okay. More important thing is, suppose both the letters are same, BB like or HH, then these are called the copolarization channels or light polarization, means both are same, means transmitted and received both are same. But if they are opposite, then they are called the cross polarization channel. Okay, like BH or HB. But for monostatics are generally BH and HB are same, but HH and BB are not same. So that is important. Then this polarization is basically, for example, here it BB polarization or HH, whatever the polarization is there. But when the signal is transmitted, let us say signal was transmitted in the horizontal polarization, but when it is reaching to the surface and interacting with different types of the features, then again it is back scattered from the target and moving towards the sensor. But when it is started back scattering from the target, then it is not remain same as it was coming from the satellite. So basically the polarization is getting disturbed after interacting with the targets. So how much interaction may be there, or you can say change in the polarization may be there. So change in or alteration in the polarization from its original polarization level, that process is called the depolarization. Okay, so somewhere sometimes, or you can say there are the targets which are not which are basically not able to alter the um, uh, initial polarization. So those are called the coherent targets. Coherent target means whatever the energy was incident, means whatever the polarization of the incident energy is there, same polarization they carry in the back scatter signals. Okay, it means after interacting with the target, polarization is not getting disturbed. It means the target is coherent target. Okay, and if the polarization is changing by interacting the target, it means since the polarization has changed, it means the target is not coherent. That is called the incoherent target. Okay, so there are two types of the targets, coherent or the incoherent targets. Coherent targets, you can say the persistent target also, or the deterministic targets also. And the name of the incoherent targets may be distributed targets or the stochastic target. Okay, so just keep in mind there are this variety of targets on the surface. So they have varying degree of depolarization. Depolarization means the initial polarization of the signal is disturbing, or polarization level is changing. How much it is changing? So that is called the depolarization. If no change is there, it means depolarization is zero. If disturbance is more, then you can say depolarization is large. So the depolarization is not good thing actually. So what happens if have a targets which is disturbing our signal a lot, or you can say the polarization level is changing a lot. So that may be a problem for the investigations. Like if we want to extract some useful information, but signal is depolarizing after interaction, it means that can create a problem for extracting the useful information. So we are ensuring like the depolarization is not there with the signals. If it is there, then we will try to improve the polarization level. Means we will try to correct that. Okay. But there may be a target like after correcting, still some depolarization levels are there. So basically, depolarization is not good thing, but since different types of the targets are there, because of that some level of depolarization will be there, and that basically we have to handle very carefully. So this is the choice of the polarizations, like single or dual polarization. Suppose different types of the data sets are available. Few satellites are there which are acquiring basically only data in HH polarization. Then you can say that is single polarized data set. Okay. Some satellites are giving only BB polarization. Then again it is called the single polarized data set or single polarization data. Okay. So either HH or BB or BH or HB, any of the form, but single is there, then it is called the single polarized channel, or you can say single polarization data. But if data is of this form, like two combination of two at a time, like HH and HB, okay, means two channels are there. So this is one, this is another one. So this type of the data set is called the dual polarization channel or dual polarized data set. So it may be like HH and HB, HH and BH, or HH and BP. So you can see in each combination two polarization channels are involved. That's what this data set is called the dual pole data. In short, we call it the dual pole data. Similarly, the BB or BH, BB or HB. So two polarization channels are combined, but there are satellites which can provide the data in BB, means two polarizations also. So those data sets are called the dual pole data sets. But yes, multiple polarizations are also possible, like HH, HB, BB, and BH. All are basically available together from a single satellite, like HH plus HB plus BH plus BB. Okay, so this is mentioned twice, but this is four only. Okay, so means all four possibility: HH plus HB plus BH plus BB. All four channels are there. So this is called the fully polarimetric data, or it's called the full pole data, or it is also called the quad pole data. Okay. So, but if you want to differentiate the physical structure based on these scattering phenomena, then we can say the alignment with respect to the radar. Okay, means how you can decide whether the signal is horizontally polarized or the vertically polarized. Okay, because horizontally here on the earth surface we can see if it is along the earth surface, then it is horizontal. If it is perpendicular to that, that is vertical. Okay, so here we are taking as a reference earth surface as a reference, and that we are automatically giving the name, this is the horizontal, and the perpendicular of that is called the vertical. Okay, but this reference is not there with the satellite. So there basically, if signal is coming from the satellite, so we are confused which plane we should consider as a reference, so that we can decide, okay, signal is in the horizontally polarized or signal is vertically polarized. So this reference we are basically considering with respect to the sensor itself, means the plane of the radar or plane of the antenna itself is considered as a horizontal, and perpendicular of that is called the vertical. So that thing basically we can decide, okay, whether signal is horizontally polarized or vertically polarized. And randomness of the scattering, if this thing is there, then vegetation can respond very well in the cross polarization channel, that is called the HV polarization. The point here is, if you want to investigate vegetation areas, then it is recommended that you should use HV polarization channel or HV polarized data set. Okay, and if you want to investigate like the corner structures, especially the buildings or man-made structures, then you should use HH, means copolarized channels, or the BB channels with phase angle. Okay, Bragg scattering is happens in the ocean, and for that you can use the VV polarization also. So different applications, basically different polarizations responds differently in different environments. Again, here you can see single versus multipolarimetric image. So suppose you have all these 3-4 channels, HH, HB, BH, BB. So any three you can combine together and you can generate, RGB image also. So for example, here you can say this is C band HB polarization, this is BB polarization, this is HH polarization image. So by combining all these three, you can generate a RGB image that is called the composite image. So that image basically is like multispectral image, and you can visualize all these structures very clearly. But keep in mind, the radar images are very sensitive to the structures of the targets, so they can reveal the original structures of the target. That is the beauty of the radar images. But yeah, visually they may not be good, but visually basically optical images are good, but they are not able to capture different types of the structures of the targets on their surface. But the radar images can capture the structures, just like the transmission lines are there. You can very clearly see in the images, okay, from where the transmission line is passing, okay, or some bridge is there, or some dam structures are there. You can very clearly see in the radar images, but they may be absent in the optical images, especially in the difficult time span. For example, rainy season or some cloud or night time, you cannot see from the opticals. Okay, so here you can also see the HH polarization image here, and here you can see the HB polarization. So this structure is very clearly visible in HB polarization. This is not visible in this particular. Here you can see here you are not getting very clear observation in HH polarization, but here you are getting very clear observation from the cross polarization channel. So now this is speckle. This is speckle is a kind of noise. So here you can see this image. Somewhere these dark patches are there. Flat and paper kind of grainy structures are there. So this effect is basically called the speckle effect, and this is a kind of noise in the data set. So this noise we have to remove very carefully. And how this noise is basically developing because of the some interference within the resolution cell. Suppose in the one pixel or the resolution cell, multiple signals are coming and going, and mutually they are basically interfering with each other. So because of that, what is happening, because of the interference, somewhere the intensity is increasing, means increasing from the actual intensity. Suppose actual intensity is 50, but because of the constructive interference, it is becoming 80. Okay, on the other side, actual is, let us say, 50, but because of the destructive interference, it is appearing like, let us say, 30 or 25, something like that. So you can say actual value of that particular pixel is 50, but it is somewhere it is appearing 80, somewhere it is appearing 25. So this deviation is just because of the interference which is happening within the resolution cell. So you can say the speckle is nothing but a kind of noise or a kind of error that is generated because of the constructive and destructive interference between the signal itself. Okay, and that's what somewhere the intensity unnecessarily increasing, somewhere unnecessarily decreasing. So this extra increase or extra decrease is basically called the speckle. Okay, so here you can also see just I mentioned yesterday also, suppose one signal, sinusoidal signal, another signal, they are meeting in phase, the overall intensity is increasing. If they are in the opposite phase, the overall intensity is 0 in case of destructive interference. So here you can see this if destructive interference is happening, then dark pixel you are getting, and if constructive is happening, then bright pixel you are having, because bright means high intensity, dark means low intensity. So here you can see, suppose the actual and suppose actual value is something else, so unnecessarily here it is added, here it is subtracted. Okay, so these are some extreme cases. Constructive means phase difference is 0, destructive means phase difference is pi, but the phase difference maybe some other values also between 0 and pi. So some another varying degree of interference may be available over the other pixels also. Like this one, this is not perfectly black or perfectly white, but some other color is there. But this is it means this is not purely constructive, not purely destructive, but some other phase difference is there because of the signals. That's what the color of this particular pixel is not black or the white. This is something else. So varying degree of interference is happening over each and every pixel, but the destructive and the constructive pixels are clearly visible in the images. So those things we have to basically remove out, and that is basically called the speckle removal filters. So different types of the filters are there to remove the speckle in the images. So here you can see these are the removal filters are of three types. One is called the multi-looking processing or multi-look processing. So what we are doing here, basically we are combining multiple pixels along the azimuth as well as along the range, and we are basically creating a square pixel. So but yes, the resolution of that pixel will be coarse compared to the individual pixels which was available earlier. So this is somehow also called the spatial averaging. Means we are averaging the dn value of the pixel from so many pixels and creating a single pixel value, because the resolution is now decreased. So that process is called the multi-look. There is a single look concept also. Single look means in a pixel governed by the original resolution along the azimuth and the along the range. So suppose the range resolution is 5 meter and the azimuth resolution is 15 meters. So the pixel size is 5 by 15 meter. But when you are doing the multi-looking, it means you are searching in another number which is multiplying by both these numbers. Let us say now I'm considering the 30 meters. So 35 6 are 30 and 15 2 are 30. It means we are taking the average of or merging the pixels, 6 pixels along the range and 2 pixels along the azimuth, because azimuth resolution is 15 meter. But now we are making, just because we are making the square, so we are considering as a 30. So 30 means 2 pixels along the azimuth we have to merge, and range resolution is 5 meter. So we have to merge 6 pixels along the range. So 6 pixels into 2 pixels we are merging and we are creating a square pixel. So this is called the multi-look processing. So what is happening, wherever the unnecessary and constructive or destructive interferences were happening, now because of average, because we are averaging so many pixels, so the effect of speckle is getting reduced. So the multi-looking is one way of reducing the speckle. Another one is the spatial filtering. Some filters we can develop and we can apply over the radar images, and whatever the extra is added in the pixel values, so those values we can remove. Another one is the temporal averaging technique, where what we are doing, we are basically acquiring multiple images over a period of time. Like every 12 days we are basically creating the images. So suppose 10 images are there. Now over a particular pixel we are taking the average of all images. Suppose 15 images I have taken over the same area. So if temporal average I'm taking for a particular pixel, it means that is called average of all these values acquired at different times. So that process is called the temporal averaging. So what happens? Somewhere the speckle is less in one image, some in another image speckle is high, and another image the speckle is high. So overall, the effect of noise or speckle can be removed. So here you can also see like this. This image is the single look image. So this side is, let us say, range direction. So and this side is the azimuth direction. sorry, this side is range and this side is azimuth. So here you can see how many pixels? 1, 2, 3, 4, and 5. 5 pixels along the range and 1 pixel along the azimuth are getting merged, and this single image, single pixel is created at the place of 5 pixels. So the effect of unnecessarily dark, white, that thing is removed, and another or medium color is assigned. So that way, the effect of this speckle is reduced by applying the multi-looking process. Okay, so here you can see another example of the multi-looking. The same example is there, where we are basically averaging the multiple pixels along the range and azimuth and creating a bigger pixel so that the effect of speckle can be reduced. So the speckle multi-look factors you can calculate like this. If you there are only 3 steps. First, you calculate the pixel spacing in the ground range direction. So how you can calculate? Like pixel spacing in range direction divided by sine of look angle, or you can say sine theta. Second is compare the ground range pixel with the pixel spacing in azimuth direction. So a pixel spacing you have now. Now you have the range pixel spacing in ground range direction and pixel spacing in azimuth direction. Now you just take the LCM of both, whatever the it is coming. So that is called the multi-look factor. So by calculation, you can just assume like the pixel spacing in range is 4 meter, pixel spacing in azimuth is 6 meter, look angle is 30 degree. Then the pixel spacing in ground range direction will be like this. Range direction, pixel spacing in range direction divided by sine theta. So 4 divided by sine 30, it is 8 meter. And now what is happening? This pixel spacing in ground range direction is 8 meter and pixel spacing in azimuth direction is 6 meter. Now you take the LCM of 6 and 8. So 8 3 ja 24. So 24 is basically giving you the square pixel. So the 24 is coming by multiplying 6 by 4. It means 4 is coming one another factor, because 6 4 are 24. So that 4 is coming. It means azimuth looks are 4 and 8 3 are 24. It means 3 looks in the range direction. So you can say 3 looks in range direction and 4 looks in the azimuth direction. So in this way you can calculate the number of looks in both the directions. This is speckle filtering things. Before it is appearing like this, and after it is appearing like this. So it is basically again averaging out the pixel values. So the number of pixels are there. Filtering techniques, adaptive filters are there, non-adaptive filters are there. Non-adaptive filters like FFT, fast Fourier transform filters. Adaptive filters mean like the Frost, Lee, MAP, and Gamma filters. The number of filters are there. So here you can see the temporal averaging. This is the viewing geometry. Yes, yesterday I have shown you. So like this image. So this is called basically the swath of the image. So this is the near range. This is far range. This is called the look angle, and this is called the beam width beta. Okay, this side is the azimuth direction. This is called the slant direction. This is called azimuth direction. So number of things are there. Look angle, which is here. Incidence angle. If you draw a perpendicular from here, and this angle is called the incidence angle. Then slant range, the distance from here to here, it is called the slant range. Beam width, the gap of this one is called the beam width. Swath width, the gap from here to here, this is swath width. Radius of the earth means that this is satellite position, and if you take the distance from the center of the earth, because in every calculation the center of earth is important. So the radius of earth is almost fixed, and above that this height we are basically adding it. So that is called the height of the platform. So these are three types of the angles. Here you can see very clearly that this is the look angle. This is called the depression angle. So sum of both is 90 degree. So you can say look angle plus depression angle equal to 90 degree, or you can say the look angle equal to 90 minus depression angle. Same thing is here. This angle from the perpendicular to this slant range direction is called the incidence angle, and this angle from the ground to the slant range, that is called the grazing angle, but sum of both is 90 degrees. So you can say incident angle equal to 90 minus grazing angle, and vice versa. And if you have the very difficult terrain, then the terrain is having certain slope parameters like this slope angle. So this is also called the slope angles. So this is the natural vertical, and this is the vertical of the terrain. Suppose this is the terrain surface, terrain, and if you draw the perpendicular, so this is called the normal to the surface. So the angle from here to here, here you can say the angle between this normal to the slant range is called the local incidence angle. And the angle from here to here, it is called the incidence angle. So you can say the incidence angle is equal to this local incidence angle plus this angle. And this angle is basically equal to the slope angle. Means whatever the slope is there, that's what the same angle is this one. So you can say local incidence angle equal to incidence angle minus slope of the tan. Okay. So these are different at different incidence angles. Also, we can acquire the images and we can have the different quality of images. Here you can say this is 58 degree, this is 45 degree, this is 28 degree. So incidence angle is going to decrease. So here you can see this again depends on the terrain. So few features are responding very well at a particular angle, like soil moisture estimations. If angle is varying between 25 to 40 degree, then you will get accurate information of the soil moisture. So the high or the low incidence angles are not recommended for the soil moisture retrieval. So that's what different angles are matters in terms of quality of the line. And this is the spatial resolution. Spatial resolution I have already mentioned, like this is slant range. So the resolution along this one direction, this is called the range resolution, or you can say slant range resolution. R stands for, capital R stands for range, and small r stands for the resolution. And this gap along the azimuth, that is called the azimuth resolution. So there are two types of the resolutions. So here you can see this image I have already shown yesterday. So like two targets are there very close to near range, and two targets are the near to the far range. So here you can say this is the pulse length. So if they are close to the far range, they are well separated, or you can say they can be differentiated by the radar pulses separately so that they can be clearly visible. But if they are near to the range, ground range, then they are coming into the same pulse width. It means they are not able to get separated. So you can say the range resolution is increasing from near range to the far range. So here the range resolution is coarse, but here in this side the range resolution is better. And this range resolution, especially the slant range resolution, is c tau by 2. C is the velocity of light, tau is the pulse length divided by 2, which also indicates this is independent of the height of the platform. Means whatever the position of the satellite is there, range resolution is slant range resolution is not going to change. Okay. And on the other side, if you see this is slant range resolution, if we project along the ground range resolution, then ground range gr square equal to slant range resolution minus platform height. So if we height we can calculate in terms of depression angle. So the equation will come like this. So it becomes h square in bracket 1 upon sine gamma square minus 1. So if you have the slant range resolution images, you can convert into ground range resolution images also by applying this particular formula. So from this example, you can also see, okay. So now this ground range resolution formula is similar to the slant range formula, c tau by 2, but it is divided by the sine theta. Theta is look angle, not depression angle. Okay, if you want to write in terms of depression angle, then it will be sine 90 minus gamma, that may be cos gamma. So in that case you can write c tau upon 2 times gamma. Okay, so here you can see if we are putting on different values, here the value of the gamma is going to decrease or you can say the value of the look angle is going to increase, or you can say incidence angle is going to increase. So here you can see the slant range resolution is almost constant at all the ranges or all the incidence angles or the look angles, but the ground range resolution is basically going to just calculated from this formula. So it is basically increasing. The numerical value is decreasing. So low value means high resolution. So you can say from this look angle is less, then it is coarse resolution. Look angle is high, then it is high resolution. So look angle is low, in which case if this line is there in near range, look angle is less, or the far range, look angle is large. Okay, so you can say from the low to high, or you can say at here the coarse resolution range resolution is coarse, but here the coarse resolution is high. So these things we have to basically keep in mind. So now time is over. So other things we will discuss in the another class. Okay, so now if you have any query, we can take 2-3 questions.